Welcome back to Lecture 10 in GRA 6036. Now we'll do some more simulations. We'll now imagine that instead of simulating we'll imagine that there are two populations, so that we will now make data that stem from two different populations. Since we will simulate the data, we know that that is a fact, but we'll pretend or we'll pretend to not know it. So now I've cheated a bit to save time, so I've written some code that I'll copy in. So here in this code is basically this code for group 0 and group 1 is, as you can see, more or less the same as what we did up here, but now we're doing it for two different groups. So for group 0, in both groups, we think that there are 100 individuals, and we simulate a covariate on the unit interval for both groups, and then we make these coefficients. So you can sort of see the model here. There are three unknown coefficients that we set, and we include a quadratic term, and then we add some noise. Okay, so maybe we should collect both of these to have the same. So this is also, of course, so we'll have noise, and the noise will be the same for both groups. So we'll just do that one time. So it's the same noise. Well, it should not be the same like this, but it should be from the same distribution. So this is noise 1 and noise 0. So this is noise 0 and noise 1. So we just collect it up here since it's the same thing. Okay, so well, here we can see. So now the underlying truth is a bit different than what we had in the previous simulations, because now if we plot this data, it will be a bit curved. So you can see if you do like this, plot the data. I guess the curve is, well, it's not that easy to see. So let's plot both of them. X1, X1. Okay, so now we have par MF row to get them in the same plot equals C 1 2. Well, so this is simulated data from our two models, and we can add since we know the truth, we can add the true underlying lines, so this line and this line, which are not the same. You see that the coefficients here are different. So to add a quadratic like this, there are probably many ways of doing it, but I do the following. I just make some auxiliary thing. There's a sequence from 0 to 1 with a small step length. So u is now, well, this thing. It's a vector. And then you can use the lines function, uu. So now we'll insert the true parameters times uu plus c naught times uu squared. The color red and line with 2, and it will be the same thing here but with different parameters. Okay, so now we see that, well, so these lines are true underlying lines. So these are basically the lines we are supposed to estimate. Here we see the quadratic term kicking in. It's not a straight line, or these are not straight lines. And so this is the underlying truth. But what we see is something different. So so suppose that we get the data set given by, so we'll now make a data set. So we see an X, which is X0 and X1. we see y, which is y0 and y1, and we see another covariate, which is an indicator of what group the observations stem from. So this is like good looking, not good looking in the project, and these we want to be indicators, so zeros and ones. And one way to make such indicators is to use the rep function. So if you do rep 0 and 10, you get 10 zeros. So we can do rep 0, and there are supposed to be n not of these, because n not is what's here. And then we'll do the same thing with 1. So we want 100 ones, and now we put these into a vector. So now we have our group vector. So if you look at it, it's 0, 0, 0, then 1, 1, 1. Now we collect these data in a data set that we call DD for short. So you can use the cbind function, y, x, gr. That will make, so if you run DD and look at head DD, that's our, here we have our data set. Okay, but yeah, of course it's bigger. I mean, if you run DD, you'll see the whole thing. But that's what's nice about the head function. You only see the first 6 rows and the column names. So now this DD is a matrix object, but we can make it in to a data frame by doing data.frame this. So now you can do class. So head DD, still head, and the class DD, it's a data frame. Okay, so now this is when we do read CSV something, it will give us a DD type of object. So this is our data. So suppose we are given this data and we plot x against y. So now we do DD x, DD y, and this is to make it resemble what you do when you have an actual some true data, because of course here we already made y and x, so we could only insert x and y, but now we extract them from the data frame that we just made. We plot this data. Let's do it in one plot. Par mf row c11. Well, so this is the data. So it's, well, this looks, if you look at this data, you might think, okay, well, looks good. We can fit a regression. We can fit a linear regression model to this. So let's do that. So fit. Now we'll make fit. We'll call it fit. Let's call it fit1. Even though that overwrites something we made previously. So DD y tilde DD $x, and it's supposed to be a dollar sign right here, and this is supposed to be y, and we fit this model, and then we could add abline fit1 color red, line width 2, so add this line to the model, and I mean it looks good. So this tells you, well, that we should have some idea of why, or some theoretical idea of why it might be a good idea to distinguish between these two groups. So in your project, why it would be a good idea to distinguish between the good-looking and the not so good-looking people. And it also tells you that with statistics, with statistical methods, we might be able to see things that are not visible to the eye. So I mean, here the model seems to be an extremely good fit. We could, if you do summary on the fit one, let's see. I know I'm hoping that things are so here, well, it's, highly significant and everything. So well, why not? So okay, so let's try to make a plot where we color the dots differently. So let's like 0, y1. So this is group 0, and we make group 0. They are blue. And we will add some points for the second group. So that's x1, y1. The color is red. And now we should check the y-axis. So this goes from minus 0.5 to about 3. So let's fix this. Y-lim, C, minus 0.5 to 3.2, say, and then now we plot it. And now we might be able, now we're sort of seeing that there are some differences. I mean, if you look away from these things, the red one seems to be lying higher than the blue ones. I mean, then you can sort of see that, well, there might be two different groups in this data. I must admit that it's not completely clear, so let's try to simulate a new data set and see if it's more visible with some new draws. So let's do it one more time. Here it might be easier to see. So with a new draw, okay. So well, so let's try to use regression methods to see if our methods are able to spot the differences between these two groups. So one way to distinguish between these two groups is to fit a big model to all the data using interaction terms. And now, to see that you could get these two models using interaction terms, that you should do with pen and paper, and you can also so write it down and convince yourself of why we could model both these groups using interaction terms. So this is LM. Let's just fit, first we'll fit a simple model to this data. So the simple model will take, LM simple will take all the data, so the data from both groups, so that's the Y, and then we'll let the intercept differ between the two groups. So we add a group indicator. Then we do ddx, and now we do ddx squared. So then we have to take it into the I thing. So this is our simple model. So now we have a model where the intercept is allowed to differ between the two groups, but the effect of experience is the same for both groups. Okay, so well, we fit this model, get LM simple. We can do summary on it. Well, everything is highly significant, and we do fit the big model. So this is the full thing. We can copy this code, and now we want to let the effect of our x differ between the two groups. So we do plus dd $, G, not GL, that's what you're supposed to do in the project. So here's GR times dd $x plus the same thing with x squared. So this is our full model. Yes. So now if it is, we do LM. We run a summary on it to have a look at what we got. Well, X is still significant. So now we want to test whether we are with our methods able to see that the data were actually simulated from two groups. Because we know there are two groups in the background, and the coefficients for these groups are different. So the question is, well, are we able to spot the difference using these methods? So now we are to test the null hypothesis that beta, so what is it then? So this is beta 0, beta 1, beta 2, beta 3, beta 4, and 5. Beta 4 equals 0, and beta 5 equals 0. Because if both beta 1 and beta 5 equals 0, we're back to this model, which means that there is no difference in the effect of x here on our y. So this is the null hypothesis. We know that, this is important, we know that the null hypothesis is not true because we simulated the data. But let's see if we are able to spot it. So we do ANOVA, LM simple, LM full. So okay, now you run it. And we see that the p-value here is significant. It's highly significant even. So which is quite amazing. These methods were able to spot a difference in the effect of x on y that were clearly not visible to us when we made our first plot. So this plot right here, it's hard to see that there is a difference in the effect of, x on y between these two groups. It's even hard to see when it was even quite hard to see when we distinguished between these two groups as we did here. What am I doing? So 1.5, I'm going, let's see, 1.5. I need some more space. Okay. Oh. It's, even here it's you can sort of see it, but it's not easy to see. And but of course, this is when you split it into two groups like this. This is indication that it might be a good idea to try an interaction term. Okay, so let's try something, and when I'll put the script out, and please play around with it, because now you see that we got a significant effect. So let's do the same thing, but make things more messy, because here the noise terms had a pretty small variance. But we can, since we're now simulating data, we can of course control the variance. So let's drive up the variance and see if we are then able to spot it. So now there is more noise. So the question is, are we still able to spot the signal? So let's go here. Now we're doing the same simulations, but with more noise. So we get this data now. Now we should again control the y-lim a bit. Oh, where am I? Here. Let's do 2.5 and minus 2.6 and minus 0.6. Okay, and now we must refit the models. So we do that, and then we run our ANOVA test. Well, it was still able to spot the difference, but we see that the p-value, well, this is not as significant. Okay, so maybe we didn't make it difficult enough for the statistical methods. or maybe I did something wrong somewhere. But so you can play around with this example and control these parameters. And so let's now try an example where we should, so let's go back to our variance and let's finally try an example where we should not reject the null hypothesis. So if we, so the intercepts are allowed to differ, but if we set b1 equal to b0 and c1 equal to c0, so this means that now our null hypothesis is true. So you could write this down and figure out why. And now I'm hoping that we will not reject the null hypothesis. So let's see if I'm right. And indeed, this is the p-value, and we do not reject the null hypothesis. Okay, so this is good practice. I mean, you should when you use advanced statistical methods on difficult data sets, try to simulate something and see how the things you do behave. Okay, so here we have some simulations basically mimicking the data, the beauty data set, where you can play around with the parameters. So please do that. Thank you, and good luck with the project.